Hey, welcome back to Calculus. In this first part of section 7.3, we're going to continue adding to our techniques of integration. So far in chapter 7, we've studied integration by parts and then kind of a specialized technique about integrals of powers of trig functions. So today I want to show you something that people call a trigonometric substitution. And basically, it's a technique of integration that lets us handle integrals with expressions in them that look like one of these three types: square roots of either differences or sums of squares. Okay, so I want to kind of illustrate how we algebraically handle those things. And then each one of these problems will end with a little bit of triangle trigonometry in order to kind of back sub into the original variable. All right, so let's get going. We'll focus on indefinite integrals here today and then some definite integrals tomorrow. Okay, so let's look at this first type. I'm talking about integrals that have expressions like the square root of a number squared minus x squared. Here the number is just a is some positive number. So we're going to take advantage of a Pythagorean trig identity to eliminate the square root. So by making a substitution that x is equal to, say, a times the sine of some angle, that angle is a fourth or second quadrant angle. It's kind of a technicality. You don't really need to worry about it too much. It's so that when I take square roots of squares, I can assume things are positive and don't have to deal with absolute values. Okay, so you don't really have to fret too much about this assumption. It's just kind of lurking around in the background to justify what we're doing. Okay, so let's walk through this computation that I've got written out here for us. If you want to simplify the expression a squared minus x squared under a square root, making this substitution x is sine theta, well, if x is sine theta, then its square is a squared times sine squared. Factor out an a squared out of that expression, and now I'm using the Pythagorean identity, the trig identity, that 1 minus the sine squared is equal to the cosine squared, right? So that's kind of the point of this method, is that I've replaced the difference of two squares with a single square. And again, because of our restriction, the cosine is greater than or equal to 0 on that interval. So the square root of a squared times cosine squared just becomes the a times the cosine. So the upshot of it is that the expression that involves the square root makes things difficult to integrate, gets replaced with an expression that has no square root. That's good news. As always in life, you have to pay the price for something. What's the price we have to pay here? The algebraic expression that we were given is now trigonometric. Okay, small price to pay. Let's just quickly talk about the substitution for the other three methods, and then, or the other two methods, and then we'll see. If you're given, we'll see some examples. If you're given a sum of two squares under a square root, then the appropriate substitution that you make is tangent. X is equal to a times the tangent. Again, this is just sort of a restriction to make some of the algebra that we're writing valid. So upon the substitution, x squared becomes a squared tangent squared. Factor out the a and use the Pythagorean identity that 1 plus the tangent squared is the secant squared. Our restriction means that secant is positive, so when you get done, the square root of those squares, you just get a times secant. Cool. So here's the summary. The expression that has the square root in it gets replaced with no square root, but you introduce a trig function. The third one, if the difference of squares is x squared minus a squared, so it's the order, right? So this time the variable is subtracting the constant. Then we're going to make the substitution x is equal to a times secant. Here is the most complicated restriction. Again, it just means because something is positive. I've even left out the details of the Pythagorean simplification this time. I'm just going right for the gist of it, that square root expression would be a times tangent. I would suggest you can stop the video right now. Can you insert the details that I left out for this last substitution? I think it's a good thing that you can check. All right. I'm going to slide forward. You can stop the video and pause this as much as you want. This thing you'll find in section 7.3 of your text. I just took it from there. It's kind of a nice summary of what substitution to make. Yeah, so I was indicating these things by calling them kind of type 1, type 2, and type 3. I don't think anybody else in the world types them like that, so don't expect that to be universal notation. But I think what you want to keep your eye on is that given the expression, I'm motivated what substitution to make. Okay, so if it's the difference a squared minus x squared, x is a times the sine. Sum of squares, tangent. Difference of squares with the variable first, secant. Okay, the corresponding relevant identities are written over there to help simplify that. But in all cases, the square root is removed because you're just taking the square root of a square. Okay, so now what I'm going to do, I've got 3 examples. They correspond to the 3 types, and I'm just going to compute one integral of each type, showing you the details of the computations, and then hopefully that's enough to kind of push you out of the nest and get you doing these things on your own. So here's the thing. The first example, I want to evaluate this integral square root of 4 minus x squared over x squared. So I can see that it's got a difference 4 minus x squared, and I'm subtracting the variable from the constant. So you can stop the video and go back and look at this if you want, but I'm going to let x equal 2, right? I'm taking that because 4 is a squared, so I'm going to let x equal 2 times the sine of theta. Very good. I'm going to compute my differential. Dx is 2 times the cosine of theta, d theta. All right, and now I'm going to start replacing these things. As we wrote above, go back in the table up there or back to my previous slides, the square root of 4 minus x squared is going to simplify to 2 times the cosine of theta. Okay, so let me use a laser pointer to help you see this expression, 4 minus x squared square root, after this substitution is just going to become 2 times the cosine of theta. That's why we're doing this. Downstairs, I have x squared. Well, x squared is 4 times the sine squared of theta. Where am I getting that? I'm squaring the right-hand side of my expression for x. Dx gets replaced with 2 cosine theta d theta. All right, so now I've successfully converted the integral into an integral in a new variable. There's a lot of cancellation that happens too as well, because it's 2 times 2 is 4, so that cancels that 4. So I'm just going to rewrite this integral. It's the integral of cosine squared theta over sine squared theta. Okay, cosine squared over sine squared. And now we need to integrate that. You might recognize cosine squared over sine squared as the cotangent squared. The cotangent squared of theta, right? Cosine over sine is cotangent. And then there's a trig identity for cotangent squared. You can replace cotangent squared with cosecant squared minus 1. Lots of identities involved in integrating trig functions, excuse me. It's cosecant squared minus 1 is equivalent to cotangent. And what prompted me to do that? Well, I know an antiderivative for cosecant squared. An antiderivative for cosecant squared. What function's derivative is cosecant squared? It's opposite of cotangent. Okay, the antiderivative for -1 is negative theta. And now I'm going to add my constant because I'm done integrating. So the integration process is done in this example, but now we need to switch back to the variable x. So how are we going to do that? Well, instead of scrolling, let's see how much room I have down here. Instead of scrolling, I think I'm just going to rewrite my substitution. X was equal to 2 times the sine of theta, right? So that means that the sine of theta is x over 2. Well, then in particular, then theta, if you take the inverse sine of both sides of that, the inverse sine of x over 2 is theta. So that's how I'm going to handle this. When I replace that in terms of x, I'm just going to write inverse sine of x over 2. But that leaves the question, well, what are we going to do with cotangent of theta? Okay, I know the sine of theta is x over 2. Well, from right triangle trigonometry, if you know the sine of theta, and we know that our angle is in a fourth or first quadrant, we can recover all the other trig functions. So here's how we're going to do it. I'm going to draw a little triangle. This triangle is just schematic in the sense that it doesn't really come from the problem, I'm just going to label one of its angles. It'll always be this angle theta. And then I'm going to label the sides of that triangle to be consistent with this trigonometric expression. In particular, you, like me, know that the sine of an angle is the ratio of the side opposite that angle to the hypotenuse of the right triangle. So there's two of the three sides. The Pythagorean theorem says that this third side has to be 4 minus x squared under a square root, right? Because the three side lengths of the right triangle, a squared plus b squared, has to equal c squared. So whatever this side was, if I temporarily gave it some name, I know that its squared plus x squared has to be 2. I'm just solving for that. You can ask me about the details, but for this video, I'm going to leave it like that. Now that triangle, I can tell, it tells me what any one of the 6 trig functions is. In particular, cotangent, maybe you remember, is the ratio of the side adjacent to the angle to the side opposite the angle. So from that triangle, I can see that the cotangent is 4 minus x squared over x. Yeah. So what am I going to do now? I'm just coming back to my expression where I had things in terms of theta. I'm going to write my final answer. That cotangent theta, I'm replacing it with what we just derived, minus 4 minus x squared square root over x, replacing theta with the inverse sine of x over 2 and our constant. Okay, so there is my answer to what the antiderivative of the square root of 4 minus x squared over x squared is. Nice. So stop the video, think about some details, but that illustrates a trigonometric substitution for integrals of the first type. Okay, so for integrals of the first type. You can pause and think about it as long as you want. I'm just going to keep going here. Second example, I'm just going to go through the types in order. This one's type 2. How do I know it's type 2? Because it's a sum of squares. It's a sum of squares. What's my a in the formula? A is the square root of that number. So it's 3. It's the positive square root of that. So I'm going to let x equal 3 times the tangent of theta. That's what that table tells me to do. Then I compute dx. Dx is 3 times secant squared of theta d theta. Okay. From the table, x squared plus 9, you can go through the algebra every time if you like, but this thing is going to reduce down to 3 times the secant of theta. That's what we did at the beginning of the lecture. So now I can start replacing. So I've got a 1. X squared, where am I going to get that? Well, square this. X squared is 9 times tangent squared. Yeah, the square root of x squared plus 9 is 3 times the secant. So that's what I'm replacing that square root with. Dx is 3 times secant squared, theta d theta. What cancels here? Let's clean this up. We get some cancellation from some 3's. Yeah, those 3's cancel. Looks like one of my secants cancels. So if I sort of try to clean this up a little bit, and I'm going to bring it over to the left-hand side of the page just so I have some room. Let me sort of section that off. So what have I got? I'd have a 9th out front. And then I've got 1 secant upstairs, secant theta. 2 tangents downstairs, tangent squared theta d theta. Okay, it's not obvious what to do with that integral, so I think what I'm going to do is rewrite it all in terms of sine and cosine. Okay, so 1/9, 1 over tangent squared, that's cotangent squared. Cotangent is cosine squared, cosine over sine, so I've got 1 over tangent squared is cosine squared over sine squared. Okay, and then secant up there, that's 1 over cosine. Now I can see, going back to my cancellation color, that one of these cosines cancels the one upstairs. So rewriting this thing one more time. 1/9. Upstairs I've got left with 1 cosine theta. Downstairs, sine squared. I think you should pause the video right now and ask yourself, do you know how to proceed? Because as these techniques of integration start layering together, kind of watching me do one is a little bit different than doing it yourself. Because as soon as I say what I'm going to do next, most of you are going to go, oh, yeah, that's what, yeah, that makes sense. But I think it's better, stop right now. How would you proceed? How would you handle the integral of cosine over sine squared? All right, I'm going to do it with a u substitution. So look how deep we are into this. After our trig sub, we've converted it into a trig integral, and now I'm doing that trig integral with a u substitution, letting u equal sine, du is cosine. So this is really just 1/9 the integral of 1 over u squared, du, pardon me. Right, cosine theta d theta is exactly equal to du. So for integration purposes, I would probably think of that as the integral of u to the -2. Antiderivative for that is increase the exponent by 1, divide by the new exponent. Done integrating, so I add my constant. And finally, in terms of u anyway, I can write that this is 1 minus 1/9, times 1 over u plus c. And what was 1 over u in terms of theta was 1 over the sine of theta. So I can write that as minus 1/9 cosecant theta plus c. All right, but I have to go back to x. I have to go back in terms of x. So let me remind you that our original substitution was x was equal to 3 times the tangent of theta. So what am I going to do? I'm going to draw a little triangle. Always the same picture. And then I'm going to label that triangle consistent with the fact that the tangent of theta is x over 3. You guys remember tangent is opposite over adjacent. So I should label this x and I should label this 3. By the Pythagorean theorem, the hypotenuse has to be x squared plus 3 squared under a square root. So now returning to my integral over here, I know that the cosecant of theta, the cosecant is the reciprocal of sine. So the cosecant of theta is the ratio of the hypotenuse to the adjacent side. Yeah. So that's going to be the square root term over x. So there's square root of x squared plus 9 over x. Add my constant. And for you, there's your second trigonometric substitution that we've done together. Nice. Quite involved. I'm going to kind of back up just so we can look at this in all of its glory. I hope it's not too small, but a lot of information that you're learning to process here. Just to summarize the steps, we had to recognize what type it is, so I knew what substitution to make. Some differential calculus to compute the derivative. Algebra tells us how the square root simplifies, so we successfully convert the thing into an integral in theta. Okay, working out that integral in theta involved some algebraic simplification, rewriting things, and recognizing that we needed to do a simple substitution, a u substitution. Cool. Then once we converted into u, we had to use a power rule. Antiderivative, we had to know the antiderivative of -2 with the power rule. And then we were back into theta, which with some trig I rewrote. And then finally I had to use some right triangle trigonometry to decode this cosecant term back in terms of my original variable in x. So quite a robust process, but it's doable. It's doable, one step at a time. Third and final example of this video lecture, I'm going to illustrate how you handle a type 3 trigonometric integral. How do I know it's type 3? Because it's a difference, and this time the constant is subtracted from the variable. Okay, so what do? We let x, this is from the table. This time x is going to be 4 times the secant of theta. Okay, compute its differential. Derivative of secant is secant tangent. D theta in differential form. And from the table above, the algebra, the square root of x squared minus 16, maybe you want to go through the algebra in details, but it's going to simplify down to equaling 4 times the tangent of theta. Okay, so now let me come over here and start replacing my pieces. So, well, 1 is 1, the square root term gets replaced with 4 times the tangent of theta, and dx gets replaced with 4 times the secant of theta times the tangent of theta d theta. Switch to my cancellation color. Tangents cancel, 4's cancel. It's nice. So what we really have is just the integral of secant theta d theta. From section 7.2, we talked about the integral of secant. It's the natural log of the secant plus the tangent. Okay, so what's the last thing to do? Well, we got to replace these trigonometric expressions in terms of x. We got to replace those things in terms of x. How do we do that? We take our defining equation, x equals 4 secant theta, rewrite it in solving it for the trig function. Secant theta is x over 4. Now, that's nice. I mean, that tells us directly how to replace secant of theta. It's going to be x over 4. We have to use the triangle to find tangent of theta. Okay, so it's always just a schematic triangle. Labeling the sides, the secant, that's 1 over the cosine. Okay, 1 over the cosine. So secant is the ratio of the hypotenuse to the adjacent. So I should label this x over 4. And this side is going to be, well, x squared minus 4's square root. Cool. So you can read off the tangent. Tangent is opposite over adjacent. So it's x squared minus 4's square root over 4. So the last thing I need to do is come over here and write all that info in. The secant of theta is x over 4. Tangent of theta is the square root of x squared plus 4 over 4. Good. And the absolute value is constant. So there's our third and final for this video lecture, trigonometric substitution. So I hope those 3 examples were done carefully enough to where you will be able to look at the Tier 1 practice problems, at least in the book, and give them a go. All right, thanks for listening.